In this module, we will continue with the analysis of blood test dataset. One of the findings of the previous exercises is that these data include many correlated variables, which should not be included in the model if we want to avoid masking effects. I recall you that by masking effect, we mean situations such as that the inclusion of one regression variable may hide the effect of other variables that are related to the included one. Last time, we saw that inspecting the correlation matrix is a possible solution to this problem. Unfortunately, the correlation itself fell short in avoiding more difficult situations. Indeed, by definition, the correlation matrix gives us information only about pairwise interaction, but it is possible that variables interact in a more complicated way. For example, when a column can be obtained as the sum of two other columns, or, more in general, with a linear combination of them. The problem is non-trivial since dependencies between more than two variables are difficult to inspect. If so, we can rely on variable selection methods to select the best subset of regression variables. And, among many possible solutions, a machine learning tool we studied for the model selection is the Archaic Information Criteria, also called AIC. In order to perform the model selection using AIC, we need to load the mass library. Then, for purposes that will be clear in a minute, we divide the available data in the test and training set. In particular, we define an object named training_data_training that contains the first 300 observations, which are the data we will use to train our model. Then, regarding the test set, we define two different objects. One is called x_test and contains the regression variables for the remaining 24 observations. Note that we are only selecting the columns from the second up to the last one. This is because these are the data that will be used to predict the urea value and then compare it with the true values, which are stored and saved in a vector called y_test. The first step is to fit a model using all available information. As we saw last time, in R, this is done using the lm function, specifying urea as a response variable, and then using a dot after the tilde, which is a shortcut to state that we want to use all available variables. We run the command and we save the output in an object called full_model. This is the starting point of our model search algorithm. I recall you how AIC works. We start from the full model and then we start an iterative search by removing a single regression variable at each iteration until we can no longer improve the model by eliminating any other column in the dataset. These steps are automatically performed in the step_IC function, which is implemented in the mass package we just loaded. To inspect the output, it is enough to print the result that is named fit_IAC. Furthermore, note that I specified the trace equal 0 option to suppress the output, but setting trace equal to 1, you can inspect all the different models visited at each iteration. In the end, the estimated model only contains 4 variables out of the original 10. Thanks to AIC, we managed to derive a simpler model containing less variables. The next question we ask ourselves is whether the selected model is a good one or not. To answer such question, we compare it with the full model in terms of mean square error on the test set. I recall you that the mean squared error is simply the sum of the squared differences between the predicted values and the real ones, averaged over the number of predicting points. Being an error metric, lower values are to be preferred. To compute it, we first need to calculate the predicted values of both the full and the reduced model using the predict function, which is automatically implemented in R. As an input of such function, we pass the model we want to use for the prediction, either full_model or fit IAC, and then the new set of data that we saved previously in an object called x_test. We save the outputs that contain the predicted values, which are used to compute the mean squared error as previously explained. If we have a look at the numbers, we notice that the lower, hence the better one, it is the one obtained using AIC. Hence, we outperform the full model even if we are using less information. As they say, this is a case in which less is actually more. We now move to a different setting and therefore a different problem. We need to load a modified version of the dataset we are using, named glucose_level.txt. In this version of the dataset, the glucose level is not a numerical variable, but we only have access to some labels stating if the glucose level is high, low, or average. Firstly, we want to load the data and produce a bar plot with the absolute frequencies of such labels. This is simply done using the plot function with the name of the desired variable, after noticing that we first need to cast the variable of interest as a factor. The new problem is a supervised learning problem. Given some labels, which in this case are the 3 possible levels of glucose, we want to predict the label for future patients for which we only know the values of the other variables. KNN is the machine learning tool we studied in this module to solve supervised learning problems. To fit it in R, we need to load the class package as shown in the slide. As usual, since we do not have any new patient to test our model on, we divide the data in test and training set. The idea is the usual one. We train our model on the training data, we use the estimated model on the variable in the test set to predict the new labels, which will be compared to the real ones in order to have an idea of how well our model is performing. Firstly, we set the seed in order to ensure the reproducibility of the results. Then, the model training and the prediction of new labels is performed using a single command, that is, indeed, knn. As arguments, we must specify what is the training data, the test data, and the set of labels for the patients in the training data. However, it is the final argument, the crucial one, that is the number of nearest neighbors used to predict the labels of the new observations. Then, given the predicted labels, we compare it with the true ones using the table command. The latter produces a table whose values on the diagonal are the ones that are correctly predicted. Namely, out of 15 new patients with a medium level of glucose, 13 of them are correctly classified. Note that the prediction is not as accurate as for the other labels, where only 1 out of 6 patients with low level is correctly estimated, while none of the 3 patients with high level values are correctly estimated. So the overall accuracy is 0.58, but we wonder whether it is possible to improve on such a result. One simple way to try improving our predictions is to try to refit the model using different values of k. In particular, in the picture, we show the value of the accuracy for a grid of values of k that range from 3 to 21. As you can see, there is a huge improvement when increasing k from 3 to 5. But after that, the accuracy stabilizes on the same value. In this case, we conclude that k equal to 5 is the best possible solution as it reaches the highest accuracy level without needing to rely on a complicated model.